Hello students, in this video I am discussing about the Einstein equation. Okay, in this equation generally denote the relation between mobility and diffusion constant. Okay, so in case of the semiconductor material, how can correlate with the diffusion constant with respect to the mobility at the thermal voltage, that having the relation between the diffusion constant and the mobility dN divided by mu n is equal to dP divided by mu p is equal to bt. It means dN here the diffusion constant for n-type material. Similarly, dP here diffusion constant for p-type material. So that is the significance of the dN and dP, p-type material. Okay. Next is the mu n here, the mobility of for n-type and mu p mobility for p-type. Okay, so that is the equation for the deciding of the mobility and diffusions, and we can improve this overall equation. We can write as like this: dN divided by mu n is equal to dP divided by mu p. It means dt thermal voltage we can write as like that the thermal voltage bt is equal to T by 11,600. It means we can replace here bt is equal to T by 11,600. Which bt is the thermal voltage. We can discuss as like this: the bt with T divided by 11,600. So we can replace this equation in the form of modified form: mu n divided by dN is equal to mu p divided by dP. We can write this equation as like this. Okay, in this we can just write as like this: mu n divided by dN is equal to mu p divided by dP is equal to 1 by bt. It means equation has been changed as like this: 11,600 divided by T. Okay, so dN and dP is the diffusion constant. We can directly correlate with the dN d divided by mu. It means the ratio of diffusion with respect to the mobility is directly proportional to the temperature. We can calculate the unit of this mobility to diffusion constant in terms of the voltage inverse. Okay, so we can write as like this: the overall Einstein equation with respect to the temperatures. Okay, diffusion constant of charge carrier T is denoted by as like the mathematically dN is equal to mu n bt, and similarly for the p-type material dP is equal to mu p in bt. Okay, so it is unit of the diffusion constant. We can calculate with the help of the mobility of charge carrier, and mobility of charge carrier unit is centimeter square volt second. It means unit of this diffusion constant, it means multiplication of the b is cancelled out, and diffusion constant unit of the diffusion constant centimeter square per second. Okay, next is the diffusion constant decrease with the temperature. It means suppose that you want to increase the temperature, D is increasing the temperature. That is the expression for the temperature. Suppose you want to increase the temperature, diffusion constant decrease. Okay, similarly for the germanium, suppose that you want to calculate the diffusion constant for germanium at the 300 Kelvin. So we have the expression dN is equal to mu bt. Okay, mu here the mobility for the n-type materials. Mobility for the n-type material is 3800 and BT here in terms of the BT means thermal voltage. BT means thermal voltage. It is denoted by 2.6 multiplied by 10 to the power minus 1. Put the value here and solve that. We can find the value Dn is equal to 99 centimeter per second. Okay. Another thing, similarly, we can calculate the diffusion constant for the p-type material is equal to dp is equal to 47 centimeter square per second. Okay. For silicon at 300 Kelvin, we want to calculate the diffusion constant for the silicon. Similarly, we put the value as the Dn is equal to mu n bt. Put the value Dn is equal to mu n and bt. Dn is directly we can calculate the Dn is equal to 34 centimeter square per second, or dp is equal to 13 centimeter square per second. Next, most important points for the diffusion cannot be negative. Okay. Next, in the not fractional part. This is the major important point to relate to the diffusion always positive and no fractional part. We can express the diffusion with respect to the charge carrier. Next topic, the temperature coefficients. Temperature coefficient we can classify it in a two way. First is the negative temperature coefficient. Second is the positive temperature coefficient. Okay. So we can analyze the form in the terms of the temperatures. And the temperatures, any parameters decrease with increasing the temperature, that is called negative temperature coefficients. Okay. For example, resistance and leakage current, thermal voltage, etc. Okay. So that is the role of the temperature with respect to the any parameter. It means any parameter decrease, increasing the temperature, that is called the negative temperature coefficient. Similarly, for the positive temperature coefficient, any parameter increase with the temperature, that is called positive temperature coefficient. Suppose that we have an example, thermal voltage, leakage current, and etc. Suppose that increasing the temperature, any parameter increase with respect to the temperature, that is called positive temperature coefficients.